remember. Thanks. Yeah, let's put this back to everybody. Sweet. So architecture, I was like you guys, as a beginning programmer, software engineer. Like software engineering wasn't really a field back then. You were a coder essentially and did other stuff too. But I kind of worked my way up. I went from being a contributing member to a team like you guys are on your project teams to running teams to managing devs up, and then finally at the end I was doing a lot of architecture work and consulting. So that's kind of my wheelhouse. I'm really interested in how architectures can help solve problems. The thing about architecture is it's also a great job because you get to wear the fancy suit and just draw boxes up on the board with arrows, and they give you a lot of money, and then somebody else gets to implement it. So it's like the perfect job. You just make stuff up. Oh yeah, I should look like this and this and this, and then just walk out and just wait, to hear the gnashing of teeth. So it's always a the thing about architecture is it's always a trade-off. There's you never can build the perfect solution. It just doesn't exist. And so a lot of what we talk about in here is what are those trade-offs so that when you're thinking about architectures, designing an app or something, like in the back of your head, you can say, oh yeah, like I can do this, but there's a consequence to that. And which is the most important to me? That'll inform you on which direction you're going to go with your design. It's always that way. Some things we're just like boxed in. Maybe I'm in a shop where, it's an Oracle shop. They spend a lot of money on Oracle licenses and consulting and so on. And, if I try to come in and build a solution out with Mongo and JavaScript and all of that, like they're going to show me the door because no, that's not the way we do apps here. We build Oracle applications using Oracle, 12i or whatever the number's up to these days. Oracle has a really nice application server that you can write code against. Like sometimes you're stuck that way, right? And sometimes I like thinking back on my career, like sometimes I would know that I was stuck, but I would present the alternate architecture anyway, because this is inception into elaboration. And as I'm working on elaboration documents, I am looking at different solutions. In fact, like you guys, your next assignment is for the teams is going to be to think about a couple of different architectures that you can use, mainly technologies for you guys, because it's such a small project. Are we going to use Java? Are we going to use Perl? Don't use Perl. Am I going to use Python? I always conflate Perl and Python for some reason. Am I going to use Python, Java, C++? Like, what am I going to use? And then just bang out a little bit of code to test that. That'll help you make these sorts of decisions. Like, did that work? Is it going to be tough? Is there an issue with, connecting to a database out of this architecture, whatever it happens to be? So that's kind of that's the fundamental approach box over there. You got to start somewhere, right? I have had teams come to me in years past and say, hey, can we use Wix to build our application? Wix is one of those drag and drop, build your own website services on the web. And the answer is always, are you kidding me? Which usually suffices, and they go off and do something else. No code. Yeah, why not? No code dev. Andy, it's funny that you bring that up. Like that's been a goal for such a long time. Like since I started 30 years ago, companies, every once in a while, for a while, it was BEA who did it with their Liquid Logic products. Oracle had a similar solution. IBM, of course, tried the same thing. The idea was let's allow people to build applications without writing any code. You would think that would, like, I would jump all over that. Like, why do we have to keep writing code? Squarespace, yeah, don't use WordPress for your application for the project. No, at least WordPress you can write some code. You can write plugins and so on. Where was I? Oh yeah, so like Liquid Logic and so on. Like, why aren't we there? I don't understand why we're not. We've been writing code for 50 years now in just about every single industry or domain. the, there aren't a lot of unique problems anymore. I mean, there's some maybe on the cutting edge, but on the business side of the world, those problems that a business has, they're exactly the same problems regardless of your business. You got accounts receivable, you got accounts payable, you got, e-commerce, like whatever it happens to be, reporting, compliance, all of that stuff is exactly the same at every single company. And yet, every single company has this enormous developer pool where every time they want to do something, they write it all from scratch. I just never understood that at all. We should be done. Like, we should have no coding classes at BU anymore because we're just done with coding, like, the post coding world. It just has never happened. And the tools that did come out, like Liquid Logic, they were okay to an extent. It's that they just weren't robust enough. And what would happen would be a company would buy Liquid Logic, they'd hand it to their business users because that was the end user, like that was the target. The idea being that business users know what the business processes are, and they could just drag and drop. It's like, oh, I've got, here's an e-commerce piece here. I'm going to connect that to my shipping piece. I'm going to connect the shipping piece to my reporting piece. I've got a tax piece over here. Like, they would just draw lines and arrows to indicate data flow. And the issue was that they just were never fully baked. And so the business users would get all excited about this, like, oh, we're going to save so much money by not developing apps. And then they'd try it and it just wasn't quite there. And then they just go back to writing their own apps again. I don't know if we're there yet. I actually haven't seen a lot in that space lately. Maybe we've just given up. And, there's just so many people. Everyone needs a job. So why not just code it all over again every single time? Anyway, so sorry about the rant. It's just kind of silly that we're still doing this 50 years later. And literally, like, I'm here to tell you, I've been in this industry since, I guess, 1970s, and it hasn't changed. It just has not changed. It should, but it hasn't. All right, so that fundamental approach, like, sometimes we're boxed in. Um, Other stuff like I get there's actually more interesting questions coming up. It's just that we have to ask all these questions going in. Like, am I going to reuse this software somewhere? Am I building infrastructure? Am I building an actual app? Maybe I can leverage stuff. Like, what if I start this project and I have some infrastructure pieces, like some plumbing I have to do? Maybe I got to build out a database management system or something for my application. Can I leverage that so that everyone in the company can benefit from it? That was actually one of my roles over at Blue Cross Blue Shield, working out of the, I never can remember if it was the CIO or CTO. I think it was the CTO, Rick. I'm pretty sure Rick was CTO. But I was working out of the CTO's office, and I was a member of every project team at Blue Cross for about a year. I was the, what did they call me? Something like architectural oversight guy or something. But my role was to sit in on every single project at Blue and try to move them toward reusable infrastructure sorts of things. For example, one of the big things we were pushing for was a data bus across the whole company, like an enterprise data bus, to share data among all the groups and even outside of Blue. When I got there, all of the applications were stovepiped. Stovepiping just means that they're all kind of vertical and they don't talk to each other, because at Blue, like most companies, money flowed from the top down into functional groups. So I had a marketing group, we had, physician management group, there was billing and so on. Each group got their own money controlled by a VP, and they would just spend the money however they wanted without really looking anywhere else in the company to see what other folks were doing. So that role was oversight. It was, for goodness sakes, if we're going to spend money, let's spend it smartly on stuff that everybody can use, and we can start plugging things into, like this message bus, for example. It was a hard sell because none of the groups wanted to pay for something that they weren't necessarily going to get to use. Like, oh, I'm going to give you, it was like a tax, right? 10% tax on the project to build this message bus infrastructure that you're going to use later, but not now. It was a really, really hard sell. I don't think they ever really completed that. I left before that stuff was done. All right, so what about reuse? That's just what I'm talking about now. Let's pull this over so I can see it a little better. Nice. So that's that notion of architectural reuse. I want to build stuff that I can reuse over and over and over, even on a small scale, like your projects. I always use the example of a database pool because that's a really common thing to do. Like you might realize, oh, to scale this application more, to more than 10 users, I'm looking at 1,000 or 100,000 users. I really have to tightly manage connections to the database. And we'll do that with a pool sort of architecture where I've got a subsystem that manages requests. It receives all the requests, from the outside, and then it chooses which ones are going to get through, when they get through, marshals the results, and so on, and pushes them back out. You're probably going to have to build one of those if the app is going to scale. We'll build it in such a way that I can use it somewhere else, make it modular, make it abstract with an interface so that I can just take that code, take it to the next project, and reuse that code. And what often happens is that kind of work, as I'm sort of here in this kind of architecture space, thinking about what the shape of the application is. If I do that often enough, like, oh, I built this database pool over here. Oh, I built this thing over here. Oh, yeah, I'm going to build this one over there. And I build them in a modular, abstract sort of way. They become almost like a library for the company so that projects go faster. Like, oh, I'm building a new project. I need a database connector. Oh, we have one over here. Just use it. Because really, in most companies, like medium-sized companies especially, the um, the technology base is pretty homogeneous and doesn't change all that much. So if we're a C shop and against an Oracle database, most of our projects are going to be in C using Oracle. So I'm not wasting time basically building stuff that's reusable. All right, so let's talk about things, and these are just really these are the things we're going to have in the back of our head as we look at various architectures over the next couple of lectures. Localize. I must have been, this is my British phase. Localize. It was my English heritage coming through. The Donnas are from England back in the day. These are the things we're just interested in. And it's not that we build an architecture for safety, it's that as we're building the architecture, we're thinking about how safe is it. And safety is more about how can I isolate things that are risky. It's not that somebody's going to get hurt, it's more risk mitigation. Maybe the scaling is really risky and it is that database connector that's a problem. So I'm going to isolate that so I can work on that independently and get it robust enough so that it's kind of quote safe to use for the rest of the architectures. I'm big on performance, as I've mentioned before, because that was kind of my bailiwick back in the day. So I'm always thinking about how do I, here's another S, how do we build a system that's performant and still meets the user's needs? Because sometimes those aren't the same. The users always want to do more than they probably need to do. And the challenge is to do all of that in a way that isn't sluggish. I don't want a lot of lag on my app because it'll annoy people. So I'm constantly thinking about performance. And in fact, as we go through a bunch of these shapes, I'll ask, like, where's the bottleneck here? When I say bottleneck, I just mean where does it slow down? What's the pinch point where the flow of data slows down to a crawl? Let's start talking about architectures. There's a 4 or 5 in here that we'll talk about over the next 2 lectures. So we'll just hop into them. This is a data-centered architecture. It's a really common sort of thing. And I guess this is so abstract that you could probably devolve any running application into one of these, this one or the next slide coming up, because these are really abstract. The notion here is that I've got some data store in the center of all of this. So that's going to be a database, probably a database. And it really is just a data pump. It receives a request for data and then returns it to these clients. Excuse me, these are thick clients. And the the way we look at the client side is if the client is doing most of the work. So if the computes are out here on the client side, let's draw that shape. Oh, I have an arrow here. I'll just use my own arrow. So the computes are here. Text. Computes are client side. So all the computes are client side. Those are thick clients. This actually was I guess it was sort of the second wave of widely deployed architectures. The next slide was the first wave. And when we talk about the next slide, I'll hop back to this and we'll talk about sort of the pendulum effect of how these architectures flip back and forth. Let's just talk about that. And I'll talk about both kind of at once. Here's the other view of it. So in this architecture, the application is in the center of this, and the clients themselves, these are just view. And just stick a view in there. Whoa. Client is shape. Client is the view. So in that kind of architecture, the work's being done in the center. And so these are thin clients. The client itself really is it's just displaying what the application is doing. So the two just vary in where the work is being done. The client computes are on the client side, thin client, the computes are in the center at the application layer, and this data app over here. And we just keep bouncing back and forth. Like every 10 or 15 years or so, we bounce between these two kind of generic architectures. So for example, in the 50s and the 60s, and actually even into the 70s, early 70s, this thing in here was a mainframe. So I had this big hall in here. It's hard to do. That data app was a mainframe usually. That did all of the number crunching, and the thin clients were just dumb terminals. Text boxes everywhere. What I need is a whiteboard. So they were mainly dumb terminals, often green screens. A green screen is just, I'm sure you've seen pictures of those, right? Find one for you. Screen, images, these things. Nice. Or maybe terminal. That's better. So these sorts of things. Access did not. Ooh, an 1101 arrow. That was pretty cool. Open the image. That thing. So that's a green screen. i5 OS, really. I wonder what that was running on. IBM Corp. Oh, you know what this was? That was probably ZOS. Yeah, that was probably a ZOS machine. Oh, and there's, I guess so. An 1103 or something. So this is a green screen application. This is really typical of a lot of industries still. If you walk into a bank and look behind you have to do it subtly, like look behind the teller's desk or, in the back offices at the bank, your insurance company, the motor vehicle registry, like airlines, like they're all using this kind of application where all the work's being done in some central location. And the interface to it is this is called a green screen because it's green. Most of the time, the terminals were just using green phosphors because it was cheap. You didn't need a lot of stuff in front of you, right? Just needed a screen and a keyboard. You don't even need a mouse for this one. And so you got the cheapest thing you could. And usually the cheapest was one color, and green was the cheapest color to make. So everybody had got green ones. This one's fancy. Okay, this is an RGB screen. to use this kind of thing, you pick numbers. You literally, it says, F4 for a prompt. So if you need a prompt, you hit F4. If you want to retrieve something, it's F9. If I want to see what the files are in the system, you hit F4 and so on. The nice thing about this is that it becomes muscle memory. If you don't change the interface, the users get really, really good at using this kind of application. It's much faster than a mouse because you don't have to lift your hand. You can keep your hands on the keyboard, run the entire system without moving your hands. If I've got a mouse-based system, I got to pick up my hand, hit a trackpad, move a mouse or something, and it doesn't jump directly to the right spot. So I got to like home in on it. It takes a lot of time to use a mouse. Like the mouse it's an okay input device. It's not a great input device at all. I think you remember, oh my God. As you get older, you start remembering stuff from your past. Like it just pops into your head. So I remember being at a company, I was doing documentation at the time. I wrote an entire chapter. It was like 30 pages in this user manual on how to use a mouse. What is a mouse? What do these buttons do? How do I move the mouse around the screen? Like that sort of thing. Because before that, we didn't have them. And this application I was documenting was sort of at that transition period where mice were becoming more popular, but no one knew how to use one or what they looked like even. I had to write an entire chapter on it. So this is green screen. That's this kind of thing. I've lost my slides here again. Tiling. I guess. What do you mean, like just put them all on the same screen? Just tile them all out? You guys are weird. That's this. So the dumb terminals are the thin clients. That is probably both, man. And then this is the thick client. What happened was we started here with mainframes in the middle. And then as technology progressed, we went from like big room-sized mainframes. We started shrinking those things down. So I joined Digital Equipment Corporation right around the time that we were transitioning from the big 11780s, which was their large mainframes, into what they were calling microvaxes. The microvax was it was the size of the micro fridge that you guys have in your dorms, sort of that chunky kind of size. But it was just as capable of the mainframe. It was a lot less expensive to buy. And a lot of companies were starting to deploy these smaller computers into their user areas, maybe not one per user yet, but at least one per floor or one per group or something. They just had a lot more compute power. And so we started seeing the computes coming from the back end, from the data side, moving toward the desktop because the machines were more capable. It didn't make sense to do thin client at that point because now I've got a machine like right next to my desk that's just as powerful as the mainframe in the back room. Like, why should I have a dumb terminal, doing that? Why don't I just move everything into that little that mini Vax or whatever, the smaller machine that was just as capable. And then that kind of evolved into desktop PCs, around mid 80s or so. We just started moving the computes from the back end into the front end, and it started to look like this. So the thick clients, now these thick clients are PCs sitting on a desktop. They're a mini sitting next to a desk, like a lot of compute power locally. And now I don't need to do those computes anymore on the back end. So now I can just use the back end as my database, my data store. Well, it just swings, right? So now we're seeing more of like, let's push stuff back to the back end. So that was kind of when the web came out in the 90s, mid 90s, like now all the computes for the web sorts of applications, they were all being done on the web server. And it looked like this again. And the thin client in that case was the web browser. The browser had no capabilities whatsoever. I'm talking Netscape, Mozilla, the early Internet Explorers. They just didn't have any facility to compute. They could display stuff. They could render HTML all day long. And so the model looked like this now. I had thin client again. I had the application in the middle. Now the application is the web server. The web server probably has a database attached to it, but it did all of the work. Every time we made a request to the web server, it crunched a bunch of stuff, hit a database and so on, and then pushed out to the clients just HTML to render. So again, that was just display. So we went from, the mainframe, and now I got micro computers and local PCs, and now I'm back to doing all the work on the backside. And then in 2000 or so, when Brendan Eich and those guys came up with JavaScript and then Node later on, Brian Dahl came up with Node. Well, guess what? Now I've got capability in the browser to do all these computes. And so now this is what the world looks like again. We're just pushing JavaScript now to the browser side for web applications. All of the work's being done on the front end, the local desktop, and the back end really is just data. In fact, this is what your projects are going to end up looking like. The back end really is just responding to data requests, and all the crunching is being done on the client side. And unfortunately, it's being done on the client side is going to be done in JavaScript because that's all you've got. So somebody on your team is going to have to learn some JavaScript. Maybe if you're lucky, somebody's had 4.12 with me. And then they can do all the work, right? You guys can just sit back and, hey, you're doing a great job. Oh, it's amazing. I didn't even do that. That's remarkable. Just keep them feeling like they're doing a good thing and feel good about themselves. They'll just keep working, right? All right, so that's kind of the evolution of this. And my guess is that like 10 years from now, we'll be back to this, right? Because it literally just keeps doing this back and forth. And a lot of that is just, like kind of the way we've set up our economy. Like there's this constant upgrade cycle, especially in technology. There's an expectation that every 10 years or so, you're going to completely revolve your technology stack because new stuff comes out. It's faster, not necessarily cheaper, but it has more capabilities. And if one company in your industry buys into that and starts building apps that, kind of kick your ass, well, then you're going to buy into it too. And so there's this constant cycle of upgrades going on. I mean, we see it in every industry, really. And except some of the old industries, I guess. I mean, is that good or not? I don't know. It feels like I've come to a point where I just feel like it's all just too much. Like, why do we need another 100 Flappy Birds, when we have one and it's just fine? Like, let's just use what we have and kind of worry about the other stuff now. But I guess if that were the case, you guys wouldn't have any jobs. So it's gonna swing back at some point. Am I gonna see it? I actually probably will. I probably won't see the swing after that one because they tend to run 10, 15 years. Although it does feel like that pace is accelerating over time. So, like between 1950 and 1970, 75 even, like 25 years, we did everything exactly the same way. And then, in 75 to 85, it was, oh, now we're consolidating on the desktop. And then the web came along and, the cycle seems to be shortening up. I will say that for you guys working, I think you're going to have it a little better off than we did like even 5 or 6 years ago. The pace of that revolution of product was just unsustainable. There was a point 6 or 7 years ago where most companies, software companies, even hardware companies, they were on a quarterly release schedule. So they'd spit out a version of their product. They'd have the next version already, in cycle before that one was even released. And it literally was every single quarter, consumers were expecting a new version or a new product coming out of that company. It just isn't sustainable. And then we started seeing, every 6 months or so, 5, 6 months, we'd do a release cycle. A lot of companies now are on an annual release cycle. I just think of Apple. Apple releases a new OS about once a year. It used to be every 3 months, companies were releasing a new operating system. It couldn't work for very long. Everyone was burning out. So you guys at least have the benefit of all of us burning out. So that I think the pace of work is a little less these days. All you guys with internships are like, no, no, it's still just as bad. All right, some issues with this. And the biggest issue with both of these architectures really, you can see it on the diagram, right? Where's the choke point on these things? It's in the middle each time, right? So whether it's an application or just data, that thing in the middle is going to be my performance hit. I'm not going to worry so much about the clients themselves because I'm going to tailor the architecture to match the capability of the client. But I've got this thing in the middle, that's a single point of failure. Maybe not completely failing, but it could slow down if it got loaded up. Like that's really the performance issue here in this kind of centralized application architecture. It's going to be that way whether it's thick or thin client, really. We had a client. They were doing, was it a power builder? Yeah, actually, I think it was a power builder application. Power builder is an old technology that looks kind of like this, and it was they weren't completely thick clients. There was some computes being done on the back end, but a lot of computes being done on the front end also. And it was a power company, a local power company here. Might have been NSTAR even before they changed their name. But the issue that they had was that in the mornings, this is down in Waltham. In the morning, they had a big parking lot at their headquarters or whatever, and all the guys would come in their trucks at 7 a.m. or so, and they would pull into the parking lot and log into the system, and they would get their work orders for the day printed out in their truck, and they tried to optimize it. So these guys were the folks who climbed up the poles and worked on the pole pigs and so on. A pole pig is that gray sort of transformer that at the top of a telephone pole you see quite a lot. So they were working on pole pigs all the time, and they tried to make it so they didn't have to do one here and then drive to Framingham and do one, then drive back here and do one. Like they tried to localize them, so it was kind of a traveling salesman kind of problem. Well, their issue was that it was architected like this, and as their business grew, it didn't scale very well because there was a big bottleneck right there in the Power Builder app. And I remember they called us in on a firefight because they realized what's happening was the guys would pull in, they'd arrive at 7. They expected to have their worksheets, like 7:20, 7:30 or so they get back on the road. Yeah, it was getting to like 8:15, 8:30, and still they weren't getting their work orders spit out. So it was really affecting their business. Like they were losing some money and getting behind in just their infrastructure work. So they called us in to take a look. I remember we walked in, we were sitting in the boardroom somewhere. It's like, oh, what's the pain here? Because we always ask what the pain point is. Constantly are asking, what's the pain? What's the pain? And the pain means, what is it about the application that is causing a struggle, or what's the issue? What's the problem, essentially, is what you're saying. And of course, the very next thing you ask what's the pain? And then you ask, how much money do you have? How much money do you have? Should have said it better than that. Like those are the two questions we always ask at every client. But their pain was pretty obvious. The next question was, let's take a look at like what you've got. Like, what is this application? What's the shape? And they showed us this. And like, okay, well, clearly there might be an issue or two here. What's the technology? And they told us it was Power Builder. Oh, I remember we were sitting up there. There was like 3 of us in the room from my company, and we just looked at each other. It's like, oh, this doesn't sound good at all, because Power Builder is just a pig. It's known as just a horrible technology. And we said, all right, we'll talk to you guys. Show us your data group. Let's talk to the apps group. We'll spend a couple of days here for free. Just, it's consulting to get follow-on business, right? We came back a couple of days later, had another meeting, and said, well, our solution would be to replace Power Builder with something else. And they said, thank you for your time, and showed us the door, because they were on really thin margins and they weren't going to spend any money at all. So out walking out the door, we're like, call Delight. They know how to do this. No, there was just like to Deloitte, because they were competitors of ours. we were constantly getting called in to clients to fix problems that Deloitte caused. And of course, they did the same for us. So it was a friendly rivalry. Are they still Deloitte? I don't know. Everyone changed their name right around the Bernie Madoff scandal. Everybody changed their names. All right, so those are those guys. The bottleneck's in the middle. Almost always the bottleneck is in the middle. Now, there's a chance that there's a bottleneck on the network because these clients are going to connect to the application on the back end over a network of some sort. There's a chance that there's a network issue. These days, at least around here, networks are fast enough that we can kind of discount that. Unless the load is really, really severe, if I've got a really large app and a big company and millions of customers, now I might start to think about the architecture of the network. But for us, for software engineers, we typically take the network for granted. We assume that we're going to have a clean network that's fast enough to handle the load. And if it isn't, like that's kind of not our problem. That's more of an infrastructure slash networking issue. There's going to be some other group that's going to do that. Now, we as software engineers would raise that problem. Hey, you know, we have a big issue here. It looks like we're jammed up on this switch. Like, what are we going to do about that? And then let somebody else fix it. So at least, you know, we let them know what the problem is. All right, so that's the big one. Network, yeah, maybe. How would I fix that? I mentioned sharding here, but the horizontal and vertical scaling of these backends. What I mean by that is if I've got this, do I have a picture of this anywhere? I'll just have to describe it. I don't have a great picture. When I talk about shard, so these are two solutions, horizontal versus vertical scaling. Vertical scaling is the easiest one. If I'm vertically scaling, vertical scale equals add more CPU, memory, and so on. And so on. I'm basically taking a single server and I'm increasing its capacity. If I've got like a Z machine, like a ZOS sort of machine from IBM, those things have CPU cards in them. And you know, the base model might have 2 cards with 4 CPUs each, like an 8 CPU machine. Well, maybe I can add a couple more cards to it and beef up the compute ability up to a point. Like they have a limit, of course, but up to a point. Like that, I'm vertically scaling that server. Or if in case of a database, a better solution is probably to add memory to it so that I can have, we talked about that actually on Tuesday. Adding memory to a database server allows me to have more caches. And as we talked about on Tuesday, caching, a memory cache is, you know, literally orders of magnitude faster than hitting disk. So I might vertically scale with memory first and then add CPU if it looked like I had a compute bound application. And by the way, it's pretty easy to examine the running application, instrument it essentially, and I can watch it running and tell whether it's compute bound or memory bound. I can get reports out of those applications by, you know, they typically have harnesses around them. So I can plug in these analysis tools to watch the running process. And it's keeping track of what percent of the CPU is it using at any given time for a given sort of operation, how much memory is allocated, am I swapping memory like crazy, am I, you know, are my page faults really high, that sort of metric. And so I can, whether it's compute bound or memory bound. And of course, as software engineers coming out of BU, like you've done a lot of theory work too. So you should be able to model the things and predict what the choke point is going to be. Like I just never was all that great at math. And so my approach was let's try it and see what it looks like. I you know, could sort of intuit it. I just wasn't a deep math geek. So I was much more interested in instrumenting the application and examining the running system so I could tell exactly what was happening rather than just guessing with a model. So vertical scaling is a good approach if I've got basically a smaller application, and especially if it's like a memory bound sort of thing, I can just slap some more memory in. Up to a point, like memory management might become an issue if I have too much memory. Now the memory manager is going to be running more often than the app, and So that's a trade-off, right? If I'm horizontally scaling, add more servers. So horizontal just means I've got 2 servers in the back end, put a third one in, and now I have 50% more capacity than I did before. That's a pretty easy solution, especially if the application has been written so that it can be distributed that way. And in that case, I probably have, oh geez, I'm really missing whiteboards. Holy crow. Let's do a new thing. I can do some simple drawing here. There's my annotate button. Annotate. And can I just draw? I'm just going to try to draw and see what happens. So I'm going to end up with something like this, right? I've got, nice. So I got a bunch of databases back here. So this is my data. And this one's been horizontally, I've done, let me go back. Are you kidding me? My base mirror. I scaled this one horizontally just by adding databases back here. So these are DBs. Database, nice. These are all my DBs back here. But now I've just introduced a new problem. The new problem is, all right, so I'm going to scale horizontally to solve this choke point in the back end on the data side. Well, now I got multiple databases. How am I going to manage that? I almost always have to do this. So now I've got some manager here, some data manager. Sweet. That the app talks to. And the data manager now has to be responsible for managing this side of it. If I just have a single database, I probably just have a connection to the database I'm using out of the app. But now that I got more than one database instance, now I've got to have something to spray those requests across all these instances of the database. And it brings up questions like this. All right, so I'm scaling by adding capacity on the data side. How am I doing that? I could just slap a whole bunch of machines back there with the same database on them, in which case this manager is more like a big IP kind of machine. Big, there's probably a way to type in here too, huh? Nice. So a big IP kind of structure, big IP is a brand. It's what folks like Amazon and Google and so on use. It's like if you think about Google, right? Google.com. I'm going to go, I wouldn't go to Google.com. I go to Amazon. So I go to Amazon.com to look at something and I just type Amazon.com in my browser. Well, there's only one IP address for that. There might be a pool of, small pool of IP addresses, but on the client facing side, it's a single IP. You can probably see one. Escape, can I do it this way? So I have to stop that? What do I have to do? Zoom is so annoying. So Amazon's at one, or at least this one, 104, 110, 159, 148. Like if I do an NS lookup on it, so we get this back, right? So Amazon.com, www at least, like that's their canonical address. That's a single address. That's their client-facing IP address. Well, they've got boxes similar to, that's kind of cool. They get this sort of big IP sort of situation. It actually looks similar to this stuff, where instead of databases, those are their servers on the backside. And what the big IP box does is it takes the traffic coming in on that canonical address, that 13 address in the 13 space. So it takes that 13 space connections coming in here and then sprays them across individual servers back here. So it's a multiplexer on the network side. It hides the fact that there's multiple machines. You're just connecting to a single IP address, and then that gets sprayed across a whole bunch of IP addresses on the backside. Same idea with the data. Here, I'd have to have something like that to spray the requests across multiple instances of the database. Now that's assuming they all contain the same data. If they contain the same data, now what's my problem architecturally? Now I've got a consistency problem. We talked a little bit about consistency in the sort of ACID kind of thing, right? The data needs to be consistent after any single operation. Well, if I've got identical data here and here and here, and through this kind of database manager, I'm connected over here and make a change. What do I do about these guys? Because now the data is not the same. So do I do like a write through kind of thing? It's almost like a cache, right? Is it a write through? Is it a write back? Typically, I'm going to use mirroring software on the backside. Oops. Annotate. Draw. I'm going to use mirroring. Oh, there's a way to type, isn't there? No, it's gone. Oh, here it is. Text. I'm going to use mirroring on the database side typically in this sort of situation. There's going to be a box back there. Let's draw. There's going to be a box. Screw you. Draw. It won't draw and escape. Draw. No. Draw. There's going to be a box back here that does mirroring across the databases. So it's going to be responsible for noticing that data's changed here and then updating all the rest of the databases. But there's going to be latency there. So one thing I might think about is, all right, there's going to be latency across these database instances on the back end. How do I mitigate that problem? Because what I don't want to happen is, a user coming and hitting this database, let's say it's Amazon, so it's a shopping cart, right? So I've got a shopping cart sitting here in this database, and I'm working in that shopping cart. And then I click on something else on Amazon, and for some reason, the big IP manager or this data manager has me going over here now, over here. Well, now this data might be inconsistent between the database instances. And so what I'll probably do is have an affinity kind of thing. Text, affinity. And what affinity is going to give me, I can't move that now. No, I can't. What affinity gives me is, it's like being sticky. So if I hit this and it directs me to this database, the next time I hit Amazon from my IP, it's going to know that it's going to direct me back to the same database. So I'll have affinity on the server side, and that's to mitigate the issue of data inconsistency because I'm mirroring the databases. And anytime that I mirror, I've got to worry about latency in getting them all to the same state. Using an affinity that way makes a lot of sense. Actually, Google does this for their search engine for a slightly different reason. Like, they have the same notion. They have a big IP kind of machine that you connect to a single IP address. It sprays your request out to a Google like search instance. The next time you hit Google within some time frame, like 10 seconds or whatever, or a minute, I don't know what the number is. The next time you hit it, you're going to have affinity on that search instance. So basically, you're coming across to the same database. The reason they do it is what they found in their research was that when you make a Google search, there's almost always a secondary search. So you do one search, and if you don't see what you need, you might refine that search slightly or search for something related. What they found was that they could speed up search response by prefetching a lot of things. They could anticipate that second request. You hit the server with your search, it pulls that search result out, but it also does kind of a locality of reference kind of thing. It pulls out other stuff around that that's related and caches it, so that on that secondary request, you're pulling from cache. So they use the affinity and big IP sort of notion of spraying traffic across multiple servers. They do it for performance because they want to cache results that they think you might want next, which I think that's really kind of cool. It's a great architecture. Ay, ay, ay. I mean to talk like so much about that, but that is a pretty fun discussion. What do I have now? I can't get out of this now. It's the issue. Annotate. I got to clear it all, unfortunately. Well, you guys will have it on video at least. Yes, no, you should have done that in a box or something, huh? Yeah, I got to clear them all. All right. Now I'm still, still with the annotations. Thank you. All right, let's talk about another data architecture. How about this one? This is a much more interesting architecture. It's trying to solve a different problem. So the first that problem was I got a bunch of data in one location in the middle, and I want to provide access to a bunch of clients in a performant kind of way. This is kind of the opposite problem. The problem here is that I've got data all over the place. I got data down here, I got data down here, I got data down here. These generally are called beds. Text. Oh, there's my text. Get rid of that one. These are beds. Back end data sources. So I got a bunch of beds on the back end here on the bottom side of this this XML abstraction. Like this one might be, maybe that's a Sybase instance. This is a Mongo kind of thing. This might be just flat files sitting on a file system somewhere. Like who knows where those are coming from? A spreadsheet on somebody's PC. But I've got a whole bunch of data on different databases, different data locations, and I want to hide that complexity from the client. From the client standpoint, the client wants to make a single request down into this application server. The application server then is going to pass that request on to a piece of middleware, and the middleware's responsibility is to fan out that request. Fan out just means I'm taking a single stream and making multiple streams out of it. So it's that middleware piece that decides, oh, this is a request. The classic is like I'm on Fidelity, for example, and I want to see my accounts. Like a bunch of accounts. I've got brokerage accounts, I got retirement accounts, I've got other accounts there. Maybe I've set it up so I can see my credit accounts. Like who knows? I have 4 or 5 accounts at Fidelity. I want to see them all. Plus, I want to see my kind of demographic information, name, address, phone number, tax information, and so on. Well, in most large companies, that kind of information lives in different places. At Fido, all of the trade stuff was coming out of Oracle. All of the demographic information was coming out of Sybase, I think. And they had a mainframe for from other stuff, like it was just everywhere. Well, you don't want to have to write an application that knows that. If I'm writing the app to build that page, that kind of single view of all my accounts page, as the application architect, I should not have to care where the data come from. That's not my problem. My problem is I want to make a request, get a response, and display it in some logical way. All that stuff should be hidden, which means that, and it might be that I'm the guy that ends up doing this. I need this piece right here. This middleware piece abstracts out the data on the back end. I don't know there are multiple beds from the app side. I know there's a single request and a single response, which means that all of that complexity gets pushed down into this middleware layer. This is the part where it's like, oh, you want to see your accounts. This part of the account comes from over here. This part of the account comes from here. This one comes from here, and so on. It's this layer that does it. Below that dotted line. Above the dotted line, it's a single request. Below the dotted line, it's multiple requests. And then coming back, when this stuff comes back from the beds, it's below the dotted line in the middleware that kind of concatenates all that. It groups it all back together into a single response based on the responses from all of these multiple backends, and then presents the client, the application in this case, it presents the application with that single piece, that single response. Well, this is a beautiful architecture. Like I use this kind of architecture all over the place because it just makes a lot of sense. This abstraction layer right here, remember I said earlier, if we can leverage stuff for the entire company, like if I can build this middleware in such a way that any application that we build in the company can just make a request into that middleware and get a response back, that's a massive win because I've just taken the responsibility for that out of the app side and placed it in a single place. I might have 10 different applications that all need this functionality, and I've taken it out of those 10 and placed it in this middleware chunk. It means the middleware is going to be complex for sure, but I've only got one place to work on it. If I need to make an update to how data is returned, I only have to do it in that one spot. On the top side of this, the top side of the dotted line, that's going to be a standard language. I've got XML here. We could use JSON, anything that is a standard format for something like a request or response. Now, most large companies are going to use XML here because XML is more strict. I can define specifically what a request looks like, what a response looks like, what pieces are required, what are not, what types, this particular field in the response is an integer. I can define those sorts of things and enforce them also. I'll toss an error if I try to pass back a string instead of an integer. So I push the complexity here into the middleware, and then I provide a standard interface using something like XML so that I can just construct XML requests and get XML responses coming back. And XML is really easy to parse. It's a very strictly formatted system. So like I know exactly what those things are going to look like coming back. And we have tools. There's tons of tools around XML. I think I mentioned XSLT, which I never can remember what it stands for. XML something something transform something something. But I can take the XML, run it through an XSLT tool, and spit out any shape of data that I want. So XSLT does the translation between like an object and XML, or a report and XML, just text or whatever. Or I could translate it into some other data format if I needed to store it locally, that sort of thing. So I'll use XML and XSLT here. Where's the bottleneck on this? The bottleneck meaning, where is it going to slow down? So generally speaking, if somebody asked you that on an interview, like they'd put this architecture up on the wall and say, where's the performance issue here? Almost always, it's a single point. Like I would say it's right here. So this middleware piece, that's playing a massive, massive role. And at least in this drawing, I've only got one connection into that middleware and one middleware piece. It might be the case that I need to take this middleware chunk and horizontally scale it. Like have multiple pieces of middleware, but it would almost look like this now. So I would like this whole bit, these would all be middleware pieces with a middleware manager sitting on top of it, like an abstract middleware manager. And then the middleware manager, when it got a request, would decide which concrete middleware instance down here it was going to pass that request down to. And then below this, I'd have all the beds. So it'd be an extra layer in here if I tried to scale this horizontally. Scaling something like that vertically, you can only go so far vertically scaling because machines are physical things and they only have so many slots for memory or CPUs and so on. So at some point, I'm going to bump up against a performance ceiling. Scaling horizontally makes more sense because I can put smaller machines in, just put a bunch of them. Probably cheaper to do than vertically scaling, especially something like a mainframe. So this thing is this call and return architecture. It's trying to solve the problem. And I'm saying this specifically because there's a quiz at some point that has this wording on it. Call and return architecture is trying to solve the problem of marshaling multiple backend data sources. I'm trying to hide the complexity of the beds from the application. The downside is I now have pinch points here at the middleware connection, but it's kind of like that disadvantage is outweighed, overshadowed, it's over something. It's mitigated by just the ease that I have now of if I need a new kind of query, I write the query here in the middleware, and then I provide an XML interface into it. So it just makes so much sense up here. And I no longer have my applications having to talk to every single database because that's not an application sort of thing. Applications, in most instances, are business things or business rules that we're implementing. I shouldn't have to care where the data came from. What I do care about is what I do with the data that is correct and so on. but I shouldn't at the application architecture level have to worry about where it came from. It just is there. Yeah, cool. Let me just say one more thing because I got a minute. This notion of abstraction, where's my text? Abstraction. Using abstraction in architectures is like we almost don't do it any other way. Typically where we start is at the abstraction. So like this, like as the app developer on this side or the app architect, I would abstract out the data completely. I would just not even care about the data side, but I would have a data box in my architecture. It's like the data's coming from somewhere. Where's it coming from? Don't know. You care? No. It's just data. I don't care where it came from. So I'm abstracting out the idea that I've got data. I might abstract out the idea that I've got a logging system to log requests. Oh, how are we going to log it? I don't know. We're going to log it. Like, who knows? Am I going to write it to a file? Am I going to print it out on a printer? Am I going to call somebody on the phone? Hey, somebody just bought something. Like, who knows? Like, do I care from the app side? No, I don't. I want to log. I want to write to some log somewhere. Do I care what the actual instantiation of that is? Nah. So I'm going to design the architecture to log. I'll have a box that says logger on it with no details other than that. So it's just the abstraction of that. And that's where we start, at least when we're designing stuff, we start at the abstraction layer because we really, sometimes we don't even know what the implementation detail is going to be yet. Like you guys, when you're thinking about your projects, like you don't know what technologies you're going to use. So you're going to have a box that says data, a box that says server, and so on. You're abstracting that out. And then as we refine the architecture, we start to make those abstractions a little more concrete. But the question we're constantly asking is, can I leave this as an abstraction? So we tend to design to the abstraction and write to the concrete layer. But if I can leave something abstract like this is a completely abstracted out data layer, I'm going to leave it like that because it makes the application design and instantiation so much easier because I don't have to worry about all the details. Somebody's going to have to worry about the details. It might even be me. Like it might be me, my team that's doing the middleware piece, but it's not the application. The application just deals with the abstractions. All right, sure, I'm out of time already. You know, it always feels like I'm talking like 20 minutes. It's like an hour and a half. I don't know how it happens. All right, guys, so we're gonna stop here. I have one quiz that I'm gonna pass out to you guys, if not tonight, tomorrow morning, which is on data. So I'll have a data quiz coming up, 4 or 5 questions on that. You got a week or so to take that. And I do owe you guys a sample user story for your work tomorrow. And that's it. I will see you all on Tuesday. Have a nice weekend. Thank you. Thanks for coming, guys. Now I gotta hoof it
Thank you
down
so much,
to,
Professor. Have a good one.
yeah, see you. Thanks, man. Gotta hoof it down to GSU.